Okay, so let's start the first theme. So the first theme is gonna be real gases and ideal gases. And to begin with, I'm just gonna give you some equations. So with these equations that I've written down, these equations are for ideal gases. So first of all, we're going to look at ideal gases. Please always keep these equations in mind, because throughout your calculations, throughout this module, you're going to use these calculations. So always keep these equations somewhere nearby. So the first one is what we're going to start with is this one. PV is equal to MRT, which I'm sure you're very familiar with as you've used it in many cases. So P is for pressure, V is for the volume, M is the mass, R is the heat constant, then T is the temperature. As we all know, PV is equal to a constant, which is MRT, for a given mass of gas. Then we're going to look at the change in enthalpy. So the change in enthalpy, which is change in H, which is specific enthalpy, is equal to Cp times change in T, which Cp is the specific heat capacity, which is at a given pressure. So Cp times change in T, we're not with the ideal gases, the pressure does not really affect the enthalpy much. So that's why we use Cp. Then the temperature is what affects it much, so we use the change in temperature, which gives us the change in enthalpy. And then we're going to have the change in internal energy. The specific change in internal energy is equal to Cv times change in temperature. So Cv, that's the specific heat capacity at a given volume, and then the change in T is the change in temperature. Then how we find enthalpy if we only have the temperature and the internal energy. So enthalpy is equal to U plus PV, where the V is the specific volume. Then if we have another way of finding the enthalpy, instead of us using this formula, what we just do is we say change in H is equal to change in U plus change in RT. This formula comes when we put this formula, and this formula together. So if you have these values, you can find out what the change in enthalpy is. Then the change in entropy, specific entropy, is equal to Cp ln T2 over T1 minus R ln P2 over P1. So T2, that's the ending temperature, T1 is the beginning temperature, P2 is the ending pressure, P1 is the beginning pressure. Then we already know what Cp is and we already know what R is. Please, these equations are only valid for ideal gases. Please take note of that. Then if you do have tables which are given to you in the thermodynamic tables which you've been given, please use the tables, as it is easier to use the tables and the tables are very accurate. Now we're going to look at real gases. So just to make a few comparisons why some of these equations stand for ideal gases, this is because we know that ideal gases, we technically take them as they don't have molecular forces in between them. Then we also notice that they have a very low density, and then we also then for real gases, we're going to make a comparison. Then real gases, something we can see from real gases and ideal gases. So real gases have got a higher density at the same pressure and temperature. So real gases have higher density at the same pressure and temperature than ideal gases. So I'm just telling you this to understand this. It's not like you have to know it and it's going to be asked in the exam, but you just have to understand it in order for you to know how some of these things go along. Then also the real gases have got lower internal energy, lower enthalpy energy, lower enthalpy, and lower entropy. This is due to the same fact that I mentioned, which I said that we assume that the real gases, the ideal gas, does not have intermolecular forces. So for the real gases, what you have to do is, please do not use these equations. All these equations which are here, do not use them for the real gases. As we go ahead, we're going to look at how we find the enthalpy and the entropy calculations for the real gases, but we do not use this unless there's a point where we look at the Z value, which we can use to determine the pressure and the volume. But what we have to know is that, so now we're going to look at the tests, because for us to when we start calculating, we have to know whether a gas is real or it's ideal. So some of the test methods. Test method for ideal or real. So for a given gas, if the pressure is less than 500 bar, that's 500 bar. Sorry, not 500 bar, 5 bar. If it's less than 5 bar, which is equal to 500 kilopascal, we assume that the gas is ideal. If the density of the gas is less than 10 kg per cubic meter, we assume that the gas is ideal. If a given temperature is greater than, please, when you're looking at these values, please look at the units, pay attention to the units. If a given temperature is greater than 1000 degrees Celsius, we assume that this gas is ideal. If not, it's real. So if you look at these values, if these values are given at you and it's a gas, you do not have to look at other factors. When you just see this, just know that it's an ideal gas, no two ways about it. Then the other method which you can use, so we will say that this is method 1. So for this is ideal gas. Okay, so now we're going to go to method 2, which is the test of ideal or real. So with the second test, what we can use is the reduced temperature and reduced pressure using the tables which have been given in the thermodynamic table handout. So reduced pressure, if you've forgotten from your first year and second year, so we'll start with reduced temperature. Reduced temperature is equal to the given temperature over the critical temperature, which is given in the tables in the pamphlet, in the thermodynamic table pamphlet which will be given. So this is the given temperature and this is the critical temperature of the gas. Please ensure that the units of the temperatures are in Kelvin. And then for the pressure, reduced pressure is equal to given pressure over critical pressure. So the critical pressure and the critical temperatures are given in table A2 of the handout. You can just go ahead and check that. Okay, so now for the tests. If the reduced temperature is greater than 2, then the gas is ideal. If the reduced pressure is less than 0.2, then the gas is ideal. And please remember, it's not that you have to find both of them. If you just find one of them holds, even if you find TR is less than 2 but PR is less than 0.2, it is ideal. So all you have to look for is one of them. So even if you look for this and then you find that it's greater than 2, you stop immediately and you say, because of this, it's ideal. The third method we're going to use. So the third method we're going to use is using the liquid density. So if we get a gas, if the density of that gas at that same temperature, that density over the density of the gas at the given temperature and pressure. So remember what I just said. I said at the given temperature. So you look at the density at that temperature. It doesn't matter the pressure, but as soon as it turns liquid at that temperature, you take that density and you take the density of the given pressure and temperature. If it's greater than 25, this ratio is greater than 25, then the gas is ideal. Then if this ratio is less than 8, this means that the gas is real. Okay, so now we're going to use method 4. We're going to go to method 4. So method 4, for which we're going to do an example in just a bit. Method 4, we use the compressibility chart. The compressibility chart is the Z chart, which I had mentioned even here. That chart has been given to you. It is in the thermodynamic table handout. So what happens with the chart is you get the reduced temperature and the reduced pressure. So what you do is you will see on the x-axis and the y-axis, and also just on the chart you see the TR is within the graph. So what you do is then the z-axis, the z is on the y-axis, the PR is on the x-axis, the TR is on the inside the graph, and then the z is on the y-axis. So what you just do is you get the PR and TR where they coincide, you get the value of z. Then if 0.95 is less than less or equal to z, which is less or equal to 1.05, means that the gas is ideal. If it goes further than this or less than this, then it means it is not ideal. But remember that if you're using a graph, you might make some errors. So even if you find 0.93 or 0.9, please retry doing it again and try to see. It will probably give you up to 0.95. Okay. Sorry, I'll just take you back to the last, because I need to use this space. Okay, I hope you can see. Please don't mind this as we have already discussed it. Okay, so what's going to happen now is we're going to use method 4. So we're still testing for ideal or real gas. So the fifth method which we're going to use is using the van der Waals equation. So this equation is written as PR, which is the reduced pressure, plus 3 over VR, which is the reduced specific volume. Please bear in mind that on table A2 in your handout, thermodynamics handout, you do have the critical specific volumes. So if you can get, so VR, what I can do is VR is equal to the V given over the critical volume, which is given in table A6. specific volume, sorry. Okay, so let me continue the equation. Then VR minus 1 over 3, which is equal to 8 over 3 TR. So what happens with this is that you'll be given, let's say if you've been given VR, you can find VR. Let's say you've been given VR and PR, then you'll be able to find TR. Or if you don't have PR but you got VR and TR, you can use VR and TR to find PR, which will then use to find, we use the previous method, which was method 4, which we looked at, which was using the compressibility chart. Yeah. Okay, so now we're going to do an example. We're going to do an example using the compressibility chart. So with the compressibility chart, what we're going to do is we're going to look at oxygen. So this oxygen, I looked at the values which have, when you look at table A2, the constant temperature is equal to 126.2 Kelvin. Then the constant pressure, sorry, the critical, so this is the critical temperature, this is the critical pressure. The critical pressure is 3.39 megapascal. Then what we're going to use is our values is our temperature is at 300 Kelvin, and then our pressure is equal to 26 megapascal. So when we look at that, our PR, when we calculate, so what we're going to do is we'll calculate. So to find PR, we're going to have our P over PC, which is equal to 26 over 3.39. So when we calculate that, it's going to give us 7.76. Then our TR is equal to T over TC, which is equal to, like I said, please look at the units. So it will be 300 over 126.2, which will be equal to 2.377. And looking at those values, if you look at our method 2 test, which was if TR is greater than 2 or PR is less than 0.2. So this is because I'm just doing an example on compressibility charts. This is why I won't end here. But if I look at this test and I look at this test, I'll just end here. But now specifically, since we said we're looking at the compressibility chart, because I want you to know how to use the compressibility chart, we're just going to confirm, because from this I can say it's an ideal gas. So we're just going to confirm with the compressibility chart.